Ready?
Morning, guys. Good to see you. Mr. Kane here.
Morning, guys. It's Mrs. G.
Mrs. G, I think we really have to concentrate on this lesson today.
Okay, Mr. Kane. Which is going to be hard to do since it's Friday.
Yeah.
Let's concentrate.
Okay, we'll concentrate.
Concentration of solutions, Mr. Kane.
Yep, concentration. So like dilute, concentrated.
Right? Like we were talking the other day, kind of like saturated, yeah.
Super saturated.
How much solute do you put in your water?
Okay. All right, so solutions can be...
Solids, liquids, and gas, and most of this is going to be liquid forms.
Most of it's going to be liquid for us.
Right.
But the solutes wind up getting dissolved evenly, right?
Right, that's what a homogeneous solution is.
It's like we've said that like 4 or 5 times so far.
Yep, you're drinking a lovely cup of tea, so am I. Homogeneous throughout.
Homogeneous throughout, this is true. Well, the same ratio throughout, and this ratio is what's known as a concentration.
Correct.
And these ratios come in different ways to measure. Okay, so we can measure these concentrations different ways. Some people like to measure in parts per million.
Yep.
Carats is another way to measure solutions.
Yeah.
Notice that's capital K, so we're talking about alloys like gold and silver, and how we get jewelry.
There's only 1 carat women know, Mr. Kane.
24?
Yes. Darn right.
There's also another way. Now, the first 2 we're not really going to do much in chemistry, but this third one here is percent by mass, and we do that.
Yep.
And then there's also something called molarity. And molarity has to do with how many moles of solute you've got per liter of solvent. And
Right.
the solvent's usually water.
Yeah, there's a whole bunch of them. Molality, normality. We're going to focus on the last 2. Percent by mass, which is real easy, and molarity, which is also real easy.
Okay, so mass percent.
Of solutions. Now, make sure you guys keep in mind the 3 different terms: solute, solvent, solution. Remember that the solution is the sum of the solute and the solvent.
And there it is there, right?
Yeah.
This is the way to calculate it. Here we are, we got the mass percent. So the mass percent of the solute
Right.
is going to be the mass of the solute divided by the mass of the solution. And like you said, the solution is made up of 2 parts.
Right.
It's the solvent and the solute.
So if they give you mass of the solvent, mass of the solute, you got to add them up before you get the mass of the solution.
All right, so for example, we could have a problem like this. We're trying to make a solution that's being prepared by mixing 1 gram of ethanol with 100 grams of water. Calculate the mass percent of ethanol in the solution.
Okay, so you have to identify the solute, which in this case is going to be the ethanol,
Okay,
because it's the smallest quantity.
and that's the thing we're dissolving. So the solute goes on top, right?
Correct. Mass of the
So
solute.
1.00 grams.
And then the solution is going to be the sum of the solute and the solvent. In this case, they gave you the solute as the ethanol and the solvent as the water. So add them up.
Okay, so 100 plus 1, that's easy. So we're basically doing 1 divided by 101, and we're going for 3 sig figs when we're doing this.
And it comes out to be?
Oh, don't forget to multiply by 100.
Yeah.
I forgot that part.
0.990%.
So almost 1%.
Yep.
Not close enough that we can round though, because we
So-
wanted 3 sig figs.
Right. So 0.990% of the solution is ethanol. That's not a lot, but
Okay, so 0.990% ethanol.
right. And the rest is water. So almost 99% water and 1%, almost 1% ethanol.
So that was pretty easy, calculating mass percent. I don't think we need to do another one.
No, that was very easy.
That was
Part
the hard-
over whole times 100.
That was the hardest type that we just gave them. You have to actually remember to add the
Add,
solvent
yes.
and the solute.
Yep.
So we can now calculate the harder
Molarity.
thing,
Okay.
which is molarity. And by saying it's the harder thing isn't to say that it's hard. It's just that it happens to be a little bit more complicated.
Yes.
Okay, this tends to be the most convenient way for chemists to talk about concentrations of solutions.
Yep.
At least for our purposes
Yes,
in
for
regular
us.
chem. And it describes the number of moles of solutes divided by the number of liters of solution.
Okay. And again, watch the terminology. Again, it's moles of solute and liters of the entire solution.
All right, so the symbol for molarity is a capital M
Uh-huh. Which is also referred to as molar.
Yeah, you can pronounce that as molarity or molar,
Yeah.
right? Depending on the context. Yeah. So the units are moles per liter.
Which is exactly like the definition, basically.
Right. So that means that the math is going to be,
Moles of solute per divided by liters of solution.
and that gives us molarity. And if we want to abbreviate it, it's capital M equals
Moles per liter.
moles per liter.
Yep. I mean, it's all right, nicely compacted right there, Mr. Kane. You got your units staring your face, you got your mathematical computation staring you in the face, and basically your definition staring you in the face. The definition of molarity is the moles of solute per liter of solution. You calculate it, moles of solute divided by liters of solution. You can't miss. It's all right there.
So we got some pretty simple discussion points here. What's the molarity of solution made from 1 mole? And apparently this is going to be 1 liter of solution based on that flask, right?
Yep.
1,000 milliliters is 1 liter?
Yep.
Okay. So if I take 1 mole of solutes and I put it in 1,000 mils of solution, what do I get?
1 molar solution.
Right? So I get 1 mole per 1 liter. So that means I get a 1 molar solution.
Yep.
Right? Okay, and that's what it looks like, a 1 molar solution.
Now, Mr. Kane, I noticed a kind of redundancy here for your... Oh, look at that poor mole. You shoved him in the liter. Anyway, I noticed you used for units a capital M. Can we also use moles per liter?
Yeah. There's 2 ways to write this. You could write it moles per liter also as a final answer. So here's one possibility for a final answer, and here's another possibility for a final answer.
Right. The capital M or moles per liter.
Right.
It's the same thing.
And you just have to make sure that if you're putting this into, I don't know, say a quiz on Moodle, you might want to make sure that you do lowercase m o-l divided by capital L, because it's not going to recognize
Right, it is a
improper
capital L.
units.
That's the symbol for liters.
We got a 2,000 milliliter Pyrex beaker here, and there's 2 moles in it.
I would like the mole wrapped in dollars. Okay, go ahead.
The other mole is wearing a tie, has a goatee, and glasses.
That would be you, wouldn't it?
Yeah, that's what I was told.
Okay.
So at any rate, we got 2 moles of solutes in 2,000 milliliters of solution.
Which is 2 liters.
So 2 moles divided by 2 liters. So 2 divided by 2 is 1. So we got a 1 molar solution. It's the same concentration as that last solution.
Now, a couple of things, Mr. Kane. I noticed that if they give you the volume of solution in milliliters, we have to do dimensional analysis, metric conversion, because the definition is moles of solute per liter of solution.
It's always liters, so you got to convert to liters.
All right.
All right, so here's an example. What's the molarity of potassium chloride solution that has a volume of 400 mils and contains 85 grams of potassium chloride?
Whoa, grams? All those other examples were all moles. Where'd the grams come from, Mr. Kane?
See, this is why I said this version was a little bit harder.
So...
I don't have a balance in the back of my room that tells me moles of a salt. So here what we've got to do is we've got to take this 85 grams of potassium chloride, and we've got to use first semester chemistry. We got to convert from grams to moles.
Oh yeah, when we did this first semester.
And I can hear you punching buttons on your calculator. You're calculating the molar mass of potassium chloride, I'm figuring.
74.55 grams, Mr. Kane.
All right.
For potassium chloride, for the molar mass of potassium chloride.
Right. So how many moles do I have?
You have 1.14 moles.
All right. So I got 1.14 moles of potassium chloride. So the molarity is going to be calculated by taking the 1.14 moles and dividing it by the solution amount, which is 400 milliliters. So I'm going to record that here as 0.400 liters.
2.85 moles per liter.
Okay, so 2.85 moles per liter.
So that literally means there's approximately 3 moles for every liter of solution.
Right, there's about almost 3 moles for every liter.
Can't get any easier than that.
So we've got 2 solutions that are 1 liter apiece. Solution A looks to be kind of weakly concentrated, right?
Yeah, there's only 3 balls in there, which represents 3 moles, so that's 3 moles per liter, so that's a 3 molar solution.
Right, if one ball represents a mole, yeah, 3 molar solution. What about solution B?
1, 2, 3, 4, 5. So that's a 5 molar solution. So you got a 3 molar on the left and a 5 molar on the right, correct?
Right. So the more concentrated solution is?
The one on the right, 5 molar.
All right, very good. Real life application here.
Yeah.
This is from an IV bag from a hospital. You can see that they express things two ways. On the top, they talk about grams
Yep.
of solution, so you could get a percent if you wanted. And on the bottom, they talk about moles per liter, except for they're talking about
Millimoles, yeah.
millimoles. Mm-hmm.
I used to make these bags when I worked in the pharmaceutical business.
Oh, yeah?
Yeah, lots of quality control goes into these bags.
So when it says 181.6 millimoles per liter,
Oh, it's 181.6 millimoles per liter, let me tell you.
so that's a precision.
Oh, yeah.
Yeah. There's a lot of need for precision in this, because
Yeah.
if you put too much or too little,
You're going to screw up all your red blood cells.
yeah, you could screw up, and that could hurt somebody.
Yep. Mess up your muscles and your liver and your kidneys and just completely mess you up big time.
I think we're going to be making up solutions in class, right?
Yes.
Okay.
We're going to be making up what's called our stock solution, and then we're eventually going to be diluting that.
Okay. All right. So if we're going to make up a stock solution, we've got to know how to do it.
Correct.
The pictures here show you how to do it. What you need is you need a piece of expensive equipment called a volumetric flask to start out with.
Which are very precise.
Right. Notice that the volumetric flask has a line etched in the neck here that tells you how much liquid to add to get a certain volume.
Yeah.
And it depends on how big your volumetric flask is. Some of them come in 250s, some of them come in thousands, some of them come in hundreds. I've seen them as small as 25 mils.
Yeah, it depends. Yeah, I got a bunch of those. Depends on how much you want to make. And most of the time our liquid, guess what it's going to be? Distilled water.
Right.
Water is our most favorite solvent.
Right. But the basic idea is this: you want exactly a certain volume because we want certain volumes.
You don't do it in beakers or graduated cylinders. It's a volumetric flask because the volumetric flasks are so precise.
So the first thing you need to do is you need to figure out how much solute you need. So if you want a 1 molar solution, you backtrack the math and you take 1 mole and you turn it into grams.
Yeah, can't you just leave it as moles, Mr. Kane?
Well, if you could leave it as moles, if you could find me a balance that measures in moles.
Moles, yeah.
Right. So if I wanted a 1 molar solution, I would have to know what 1 mole is equal to in grams.
Yeah.
Okay. I would measure that out, and I would put that into my volumetric flask. After that, I'd probably make sure that I washed some water in and stoppered it up and made sure that that dissolved pretty well.
Yep.
The reason why you do that now before you fill it all the way up is because it's very difficult to swirl the water when there's water in the neck
When
up
it's
here.
full.
So you swirl it while it's still 1/2 to 3/4 full, and things get dissolved pretty well. And then once things get dissolved, then you can open it up again. You can add water until it hits the line. And you want to do that very carefully because you don't want to put too much. If you put too much,
You got to start over.
you got to start all over
Done that a lot of times.
at step 1.
And the bottom of the meniscus has to touch the line.
So, just like everything else, we read
Right.
from the bottom of the
It's
meniscus.
the bottom of the meniscus you're shooting for.
Okay. All right.
But you have to do some legwork before you start this, right? You have to figure out how much water, what volumetric flask to use. You got to do a little calculations because you got to figure out how many moles. You got to figure out what mass that is, yeah?
Right.
So you got to do a little legwork before you go grabbing a volumetric flask.